Right now I'm just giving a little presentation over here on industrial automation and distributed control on Plan 9, and I started out by working with the Modbus protocol. I guess I start off as what is industrial automation? And industrial automation, of course, is automating an industrial process that was originally carried out manually. First it started out with mechanical things, gears, levers, pulleys, cams, and so on. And then over time, as we moved into the electrified age, we went into electromechanical. And you had things like relays and motors and solenoids controlling things. And of course, then computer control came along. And right on the screen here is one of the first industrial control computers, the Modicon 084. It was originally envisioned by Dick Morley at Modicon. And his original vision for a computer, because in those times, if you said the word computer, it drudged up these images of rooms full of cabinets and needing to hire expensive engineers in order to operate them. So Morley wanted to kind of figure out a way of building a simpler computer, and he came up with one. And the idea was that there was no interrupts for processing. I/O was directly mapped into memory. And it was a rugged design that was designed to go into a cabinet instead of, it was actually designed to go into a machine and operate on a shop floor where there's going to be dust and dirt and grease and oil. And so, of course, another thing was too, is that it was important that plant technicians and other personnel were able to go in and modify these programs that ran on these computers. And one of the initial languages that were developed for this purpose was ladder logic. And ladder logic is a graphical language that, come on, eventually I'll be able to get it on the screen, which sort of looks like this. And it's pretty primitive in the sense that it represents a ladder schematic diagram that was used in industrial control for electromechanical, where you would have a vertical left and right, which represented sort of like your positive and negative of your control power. And then, of course, you would have power coming in on the left, and then you would have a set of contacts. Here we have an OR set. So if A or B is on, then output Y would be true. And of course, you would have, this is a rung, and you can have many contacts as you want. There could be comparison contacts, which could look at variables and so on. And from there, this enabled plant operators and simple technicians to be able to go into a computer that was controlling machine and actually make and edit changes. And they didn't have to know about all these other complicated processes that, were associated with computers and that were scary. And one more thing of interesting note was that Morley actually said to everybody during marketing of the Modicon machine that it is never to be called a computer. Do not mention the word computer, and if there was, he would erase it from the blackboard or crumple up the paper and throw it away. It was not to be called a computer. So I guess this, over the years, kind of created a divergence in thinking about how computing works, and it went in the direction of the discrete PLC. And a more modern discrete PLC would be something like this, which is a Siemens Dynamic, or this is a Somatic, I'm sorry. And this is actually inside of a machine at my work here. And as you can see, the processor is on the left, and then you have these I/O expansion modules, analog inputs, digital outputs, and so on. And these are all connected to sensors and switches on the glove box that monitor pressure, doors open, and control pressure solenoids that let gas into the box. And this computer now that sits inside is connected to an HMI. And if I could just get that popped up, which is the human machine interface, which is the other half of it. And sorry about this presentation being very janky. But, well, yeah, no PC present. That was actually part of a troubleshooting operation. But this is what you pretty much would look at. You would just have a very simple interface with buttons and a little readout, and it would just give you a few very fixed functions. And of course, this is very static, and of reprogramming these kind of older PLCs were not very friendly. They were very fixed in terms of function and so on. And on top of that too, I/O is sort of also kept local to it. And then from there, we went into a more modern form of the PLC that we now call the PAC, or Programmable Automation Controller. And a Programmable Automation Controller, let's try and get this over here, looks something like this. So that's a Beckhoff controller, and what that little thing is actually a PC. And it mounts to industry standard DIN rail, which is that little metal railing in behind it. And it has all these little modules that you can add and slide in and out that, again, are your analog inputs, outputs, communications modules, and so on. And of course, since it's a standard PC, well, it boots and runs 9-front. And sort of testing this out. I don't have this fully working yet. There's still a lot of work to be done. But it works out of the box, and that is pretty much the foundation right there of what is industrial automation and these programmable logic controllers. And now, from there are various protocols that are used to communicate in between all these different types of devices. For example, the protocol that's used on these little couplers here, these terminals, I should say, is called EtherCAT. And EtherCAT is something that is much more complicated than Modbus. It's something eventually I'd like to tackle. But essentially, it's just structures over the wire, and they're read in real time as the telegram or the Ethernet frame actually arrives through each terminal. There's a little processing chip in there that actually looks through the packet as it's coming through in real time. And then if it's addressed to it, it actually starts poking bits into the empty little containers that you have in the frame, which are just data structures. And this can be done deterministically, and then you can actually create real-time control systems that have cycle times accurate into the microsecond range. And you can do things like real-time motor control, servo control, where you actually close the loop on the controlling computer instead of a dedicated motor drive. So from there, it's why use Plan 9 for this? I mean, you know, if there's existing tools and software out there, why bother, right? And those tools are were historically grew up around the 1990s and around Microsoft Windows. And they use things like OPC, which is the Open Platform Communications, and that was originally based on COM and DCOM. And it was restricted to Microsoft. And it was a big complaint was that nobody could really use it on Unix or Linux at the time, or BSDs. And then so that kind of evolved into OPC UA, and that now is a cross-platform data exchange protocol that allows you to move data between controllers, computers, and so on. Let's see here. And again, using Plan 9 has a lot of advantages because a lot of these Microsoft things are big, really big. Unfortunately, I had a picture here, but Beckhoff, the maker of this controller, uses the Microsoft Visual Studio shell. And so it's a 6 gigabyte package to write code to flip a few bits. And if you think about that little ladder logic diagram I had there before, imagine downloading 6 gigabytes to write that program. So, and of course, right in the middle of it, it'll up and crash on you, or you're running it on Windows 10 or 11 today, and you come back in the morning and you found out that your computer is restarted and Visual Studio or whatever it was wasn't aware of this and didn't save your work that you may have left open or something. And of course, that's on me, but still these things, big software, big problems, you know? And so you also have the problem too where there may have been components that were stuck that enabled real time, and you cannot install these components as their drivers, they're kernel based, on newer versions of Windows. And you're stuck with Windows 2000, Windows XP on controllers, and then you're going on eBay and buying, 20-year-old Dell computers just so you could reinstall this stuff and keep it going. And after a while, this becomes more and more difficult, and it's kind of a huge treadmill that I just don't want to be on anymore. And so Plan 9 kind of eliminates all of that, these problems, because at this point, the OS is the runtime. I don't need a gigantic layer of software or middleware on top of an existing Microsoft or Linux installation. A lot of them are based on co-kernels to provide real time. And it's another operating system running your operating system as a scheduled process. And it preempts your operating system to run the control code. And again, these are kind of obtuse things that are just difficult to work with. They're not user-friendly. You really don't know how any of it works. And when it blows up wonderfully and spectacularly, and then you're just probably usually just reinstalling from scratch. But with Plan 9, you have the entire thing, you have the OS. It gives you a distributed design. I could do things like one disk can boot multiple computers. Everything could be stored, all your machine configurations can be put into the config directory. NDB can also be utilized to set things up and to configure all the different controllers. And then on top of that, in lieu of all these complicated protocols that exchange data between systems, we could just use 9P. There's no need to duplicate things such as copying just small amounts of data, whereas you could just have files representing variables. You could have files representing entire chunks of memory, perhaps. And on top of that, it gives you the ability to just use read and write to get to the data. You don't need drivers. You don't need a whole protocol stack. You don't need to worry about if your programming language has a library for said protocol. As long as your language can call open and call read and write, you have access to the data. And on top of this, too, security is built in. I don't need to worry about using some sort of weird back-off ADS routes thing where you're just adding in weird IP address stuff and all kinds of other just duplicated effort and security mechanisms that are, so they secure, who knows. And instead, now you have per process isolation. You can change the file system view right there for each and everything that you're running. You have file permissions built in, so now you can control access to the data just through the file permissions. And on top of that, Plan 9's really small. It's small enough for a single person or a small team of people to actually work with. And I'm sure there are many people in this room who are far more advanced than I am that have their own forks maintained. Now that's something that you really can't do with just Linux or all these other systems. So that fact right there, that it's small enough, it's easy to troubleshoot, it's easy to develop on, and it's easy to navigate. And on top of that, it's very portable. We don't care that we are on MIPS. We don't care if it's RISC-V. We don't care if it's x86. You just change the object type, and then you build your software. As long as we have support for it, we can run it. And that makes porting things, Plan 9 to different types of controllers that might even be existing, much easier. And once you have the kernel ported, that's it, everything else follows it. And on top of that too, since it's very small and lightweight, it runs on all kinds of hardware. I don't have to worry about if it's, it could run on, for example, I have it running on a 400 megahertz national geode with 128 meg of RAM. I mean, and that's out of the box. That's without tweaking anything. That's without building a smaller kernel or adjusting memory or anything like that. Out of the box, it just runs on these small machines. So it's easy to make work. It's easy to make it work on these different platforms. So where to start with all of this, for me at least, was to get to where I want to be in the future, where I can just use 9front or Plan 9 in general to actually run code, is starting out with Modbus. And what's Modbus? It's a field bus protocol. And a field bus protocol is used to transfer data between all these little terminals and the PLC processor itself. And Modbus is one of the first ones. It was developed by Modicon. It's a very simple, it transfers registers or bits. And registers are 16 bits. Originally, the old Modicon machine was a big Endian word machine. And so you just quite literally had a 64K word space, and you would just copy registers or memory values from one machine to another. And those can be, including, I'm sorry, this would also include bits as well, which are used to represent coils or relay coils, so to speak, and contacts, and as well as just individual discrete inputs, digital inputs and outputs and so on. So it was turn light bulb on, you would turn a bit on. And so Modbus has a few basic function codes built in that provide this functionality. There are a few function codes for reading and writing registers and reading and writing bits. So I started out with just this very simple protocol. It's very easy. The frame of it, looks like I don't have the picture of the frame. But, do I? No, I don't. Darn, sorry. But it's a very simple protocol in which it just starts out with 1 byte that identifies the function code. Then there's usually 2 bytes for parameters, usually like a starting address. For example, for reading registers, you would use function code 3. So your PDU, the actual little process data unit, the little frame you would send would just start with a byte that says 3, and then you would then send a word for your starting address, another word for how many registers you want to read, and then you would send that to the server. And the server will process the request and sit there and say if the starting address and the number of registers is correct or incorrect, and if you're good to go, it'll return that data to you. And so since it's very similar to a read and a write, I can map that to 9P very easily. And so one way I just wound up doing that, fortunately, let me see. And I wound up doing that by kind of just saying that when I just generated a file and attached a handler to that file that when you send a read to that file, it then calls function code 3. And the file offset, the seek number, the seek offset is then used to determine where you're going to start in the registers. But of course, you have to map bytes to words. And it's not that hard. You just multiply by 2 or divide by 2. And just with a little bit of math, we're able to translate a byte read call through a file and then map it to a function code to get the data out of the PLC and then return it as a stream of bytes. And I did that using a very simple little Modbus library I came up with. It only concerns itself with serializing a function code into a frame and then sending it out to the server. Server says yes or no, and then returns your data or an error. And I never bothered to put any kind of data handling in the library. It just returns bytes. So the user's responsible for dealing with that. Are they words? Are they bits? The bits actually are packed into bytes when they come in. So it was easy there. But yeah, and then opposite way of doing this, would I serve data from a Plan 9 machine to a PLC, for example. And that was the idea I had for a Modbus daemon, and that serves a file using Modbus. So I have a very small little listener that listens for Modbus frames, and as they come in, they're processed, and what I wound up doing was mapping out the file to where you would say where your registers live, where your bits live, if they overlap or not. And from there, return the data from that file as if you're looking at PLC registers or bits inside of it. And that was able to kind of make things a lot easier where you can now share both ways. So you can either read data out of a PLC, or you can serve data to a PLC or even an HMI, which is the human machine interface, or the little user interface. Let's see here. So I have, a few little working code. I don't have anything here, unfortunately, anything exciting. It's kind of at home. But that's where I'm starting at with all of this stuff. And I eventually would like to get to the point where I have a machine actually running some of this code. And I kind of have started a little bit at work. Unfortunately, this kind of machine, this is actually, you can see there, I have a little tiny little PC down there, and that's hooked up to an existing PLC, and there's just some test code up there. But this is actually the inside of an electron beam welder, and this we actually are installing, and we move this machine, and it's quite a project to put one of these things back together, as there are 1 million wires inside of them. And of course, this is also an electromechanical machine originally, and we're sort of now adding computer control into it as well. And this is like the ideal area where, well, this is what originally you looked at, tons of relays. And it's nice that you could replace all of that with just something that is as tiny as this little guy right here. And it also eliminates enormous amounts of wiring. Let's see here. There's an old panel here. Yeah, so here's the inside of an old panel. So this spaghetti right over here is what somebody would interact with. On the other side is all knobs and levers. It's all knobs and dials. The other side of it actually looks like this.
What's that device again?
It's an electron beam welder.
Okay, we're still on that.
And this machine right here, this particular panel and everything, this is state-of-the-art late 1960s, early 1970s. The person operating this machine pretty much had to know how to how to operate every single thing. So for example, an electron beam welder, it actually fires a beam of electrons inside of a vacuum. So the part has to be inside of a chamber, and that's what that is. A little window back there looks into the chamber, and the operator sits in front of it, and they look into like a little periscope thing. And so now, right over here, you would actually have to manually cycle through your vacuum. So somebody would have to sit there and look at the vacuum gauge and know when the appropriate time is and know the pressures. So the person had to automate the process, and they had to be educated about the process. So an operator not only just had to know how to weld, they had to know how the entire machine worked. And so this very manual process where you would have your motor control for moving the table around, you would have your vacuum, then you would set your beam current parameters and your high voltage power supply, and then you would even have a little beam deflection over here, which can actually, it's like a giant CRT at that point. This is actually a 7.5 kilowatt CRT. And then there's another one that we have 15, but this one right here, you would just be able to move the shapes around and the deflection around in just a circle or a straight line. And we took one and went from something that looked very similar to that. Let's see here. There we are. So you go from something like this, where it's a big giant manual panel, and this is what modern automation would give you. This is another machine. This is the 15 kilowatt machine. So now what we actually have is we have an HMI all the way off to the left that deals specifically with the vacuum system. And now the vacuum system are those two colored buttons in the upper left-hand corner. Blue meaning that you're under vacuum, and yellow would be that you're vented. And so that right there, those two buttons, which just operate some code inside the PLC, completely remove the entire need for the operator to just stand there and stare at the machine and index a knob. And of course the boss loved that, because now they can actually do more work while waiting for the vacuum. So And then, of course, the process is then automated through here with the motor control. And this is actually then created 2 fake axes, and then we wired that into the deflection amplifier. So now we can actually move the beam around via CNC as well, in addition to the table. So all of this automation right here moved a machine from basically the 1970s into the 2010s, at least. And the guy who was able to sit at this machine doesn't need to know anything other than I put the part in, I push the button. And further from that, there's even more automation that you can provide that even does things like joint scanning and tracking. This machine doesn't have it, we have one that does. And that you can literally just take anybody and it becomes a real George Jetson machine where all you just do is one button continuously. And it does everything for you, including venting and pumping down the machine. So these levels of automation here can just be done inside of a computer, and we don't need all this huge amounts of complication. Right there, there's Windows running. That little guy on the left there that little HMI on the left has to be programmed through a USB cable, through another piece of Windows software. Windows 10, basically the vendor sat there and told us that that's for the CNC control. They said, do not, under any circumstances, plug the Windows PC into the internet. Updates will immediately murder the software. So this is the kind of stuff that would drive me mad, and I have piles of Dells and even computers to run DOS and DOS HMIs. And so a lot of this stuff at the end of the day is just flipping bits, just reading and writing stuff. Industrial automation isn't complicated. A cave story has more code in it probably than this whole machine does. So at that point, you don't need these huge contraptions. I want something small and simple, and Plan 9 really gives that to me. And I can have things like my PLCs, and I can have multiple in one cabinet, and I can boot them from one disk, and I can configure them all from NDB or the config directory, and write very small, simple code, and serve all these resources, such as field buses and all these I/O points and everything, just as files. And I could bind them all into a namespace specifically for a certain PLC control program, or I could distribute them, and I can have different small little PLC processors all around the machine handling different tasks, and then they just supply maybe small little files out of them. And that's in the future for what I would like to do, is have maybe even a little PLC runtime where you could look inside of it and you could register variables in a little 9P sort of server. And then, your things like vacuum pressure can just be a file. And then it would just pop up right there, and you could open that up, and then you can read it. And if you have the right permissions, perhaps you could even write it. So you could change settings too. Another interesting thing that I thought of about that is that it would kind of allow you then to just sort of back up the PLC with things like tar or zip, where you can just go through a whole directory and just grab an entire snapshot of everything and then write that into an archive, and then there's your configuration, and there's your snapshot for that particular point in the program's execution. So yeah, this is what I've been doing and poking at little by little. Unfortunately, progress is a little bit slow, but in the future, I want to be able to get this to work on actual machines, get it to where it's stable enough, where I can just actually use Modbus to communicate with some of this stuff and get a PLC program running, start working on the other components for it. Such as maybe even like a little HMI library, some kind of graphical thing where meters or sliders or knobs and buttons and dials, and some kind of little PLC runtime, and just have a small little thing, and then from there build up with more protocols, possibly interacting with higher level stuff like MQTT, OPC UA, which is the newer version of OPC, which thankfully does not use COM or DCOM anymore. But still, when you look at these things, they're still huge. And I think I remember looking at the boilerplate to instantiate a variable on OPC UA is something like 20 or 30 lines, the integer speaks German and things like that. So you know, there's a lot of boilerplate and a lot of verbosity, and I just think it's kind of pointless when you just have 9P. And so that's what I want, and that's where I want to go. So yeah, that's pretty much it. Any questions? Sure.
So I have actually a practical question. This is one of the neat talks we get where somebody in this world is doing this, right? And the thing you always get, I'm sure you get, is, oh, but that's weird, or whatever, right? And,
Oh, yeah.
Or, but you don't get support. So this is where, now I'm sitting here thinking, suppose there's a foundation that could somehow help with, because we've never had that before, actually. We've never kind of had this advocacy and support. What thing could such a foundation do to help you make progress at your company, if anything?
I think just getting people who are probably more talented than I at programming, helping me out, giving some assistance, and just taking an interest and just kind of helping, you know, me further the software along to get where I want to get.
And the flip side, if you ever got somewhere with, well, no, I'm saying you've gotten, suppose you get to the point where this is actually ending up in use in a real world product, right?
Mm-hmm.
Would your company be open to being on the website as like case study, successful case study of actual deployment?
I would have to talk with them, but it is possible. I've thought about it. We're under new management now, and they're very open to new things. So I'm actually, that's a very good point. I have actually played with the idea of actually telling my boss and saying, well, the new president, and saying like, hey, I have these ideas, but I kind of want to don't introduce that yet until we're done with this big project here, because
Yeah.
But yeah, and of course, another thing that I hadn't thought of too is also with a lot of these protocols, you have to be a commercial entity in order to access documentation and so on. For example, the EtherCAT organization does not allow individuals to join. You have to be a commercial entity or an academic entity, and then you will then get access to documents. Some of these things you have to pay for. You have to pay for some of the specs and standards. So like access to those things would probably be something that the foundation could help with. Also certification. Any of these things are safety related. A lot of these protocols offer safety mechanisms to comply with things like functional safety, all the way up to like SIL 3 and 4. Safety integration levels, and SIL 4, for example, would be something that directly handles human beings, a train, a car. So these are very high levels of safety that, you know.
That's the scary one.
Yeah, so these are things that require, you know, you to certify. And that would require auditing code, proving, you know, that your code is correct and operational and so on. But it's a big thing, but yeah.
Do you have tools? Are there tools that you refer to for this auditing? It's not human, is it? It's really literally all human, or are there automated systems that you like to have in use for auditing?
I haven't gotten that far yet, so I really couldn't tell you. But yeah.
Do you know if there'd be any upset because it's not a quote-unquote commercial compiler tool chain?
You know, I think, see, the way I think about this is at two levels. There's the end user level, like my business there. They wouldn't give two shits what it's composed of as long as it works, right? That's the end thing. Like a lot of the times, a lot of people sell you all kinds of janky things inside of a box, and the company just buys it because it works. Yeah. And they don't care what's underneath. But I think that regulatory bodies or any place where they might be concerned there may be some end users that do require, very large facilities would require some sort of standard, at least some safety.
I can tell you for a fact, the compilers are not included in safety.
They're not what?
The compilers are not included in the safety assessment. Because they're using client GCC.
Oh, I know. No. There's the reality and the perception, right? You know how this goes, right? And so, but yeah, I totally agree.
And now third-party graphics libraries and other stuff.
Yeah.
So those are likely certified, like other with a specific graphics library content will be run through some various kinds of analysis and a lot of testing to say it seems to be okay as far as it goes.
Yeah.
It's a strange business.
Yeah, no question. Yeah. Do you have a question? Or, oh, no.
No.
Okay. This is really neat.
I just have one question.
Sure.
Do you intend or do you have used the real-time capabilities of the online kernel?
That is exactly something that I want to research out into the future, especially when you're getting into things like EtherCAT, where you use cyclic timing, where you can schedule on a deadline and you can say, for example, every millisecond run this code, and you can, or even faster than that, and guarantee that the process is scheduled at that point, and then you can do things like I was saying before, like servo updates and so on, and motion control to really get there, and it must be predictable. So, yeah, I've definitely thought about it, but I have not gotten to that point yet.
You mentioned MQTT. Have you gotten anywhere with that? I was looking at that last year for something.
Yeah, you know, I haven't used MQTT yet in my own work. I actually have been wanting to, but we don't do, like, MQTT is very useful for things that you have kind of like distributed and scattered about. We don't have a lot of things scattered about the machine. The machines are very small and local, but I'm sure in areas where there would be, for example, you know, building monitoring is probably one of a big use of it, where you would have temperature sensors and humidity sensors and so on all throughout the building. But yeah, no, that would definitely be a very useful thing to have, is MQTT for sure. That is kind of today probably, Modbus is actually very primitive, but it's still an open standard, and pretty much everybody supports it out of the box nowadays. So MQTT is sort of kind of displacing that as your sort of standard little protocol to communicate between controllers, process data. So that would definitely be a place to look today. Yeah. Haven't looked at it myself yet, the technical part, but eventually, yeah, it's something else. Anybody else? Sure.
How long before you can get a GIMP to turn off relays?
You know, I really wanted to do that too. I wanted to figure out if there's a way of doing that, you know, if you can just sit there. Yeah, exactly. I mean, that would be like cool as hell, like your HMI is Doom, you know? I mean, somebody remember PS Doom, if anybody remembers that from back in the day?
So how do you map the monsters to relays?
That would, yeah, that's something that we have to think about.
You'll let them program in Minecraft.
Sure.
The other real thought, I mean, like, so the TCP stack was originally outside the kernel, and then got pushed in, and, you know, I talked to the guy who did that about it, and, you know, essentially it was nowhere near the level of effort that you would think of from the Unix world. So for your real-time stuff, you know, there really is the idea that you can actually develop the thing entirely outside, and then because the sort of set of things that have to be done are so similar in and out, you could seriously talk about saying, oh, we can put something in a kernel and do better than, in a way, you could never do in Windows.
Right.
Because nobody wants to write Windows drivers. They're horrible, right?
Yeah.
So, I mean, there's that other additional argument when you get to hard real time that, well, if we have to, this is a kernel that's actually approachable enough to really modify for our needs.
Right, yeah.
So,
And it's the simplicity that I really appreciate about the whole system. And that's the real important part.
yeah.
And I think that would make development a lot easier and faster.
It's really interesting.
Okay. All right, thank you very much, everybody.